nirvana.
I love looking at old copies of the Royal Statistical Society Journal because it's full up with such odd stuff. There's a wonderful paper from the 1840s which shows a map of England and the rates of bastardy in each county, and so you can identify very quickly the areas with high rates of bastardy. Being in East Anglia, it always makes me slightly laugh that Norfolk seems to top the bastardy league in the 1840s.
One of the founders of the Royal Statistical Society was the great Victorian mathematician and inventor Charles Babbage. In 1842, he read the latest poem by an equally great Victorian, Alfred Tennyson. Vision of Sin contained the lines, "Fill the cup and fill the can, have a rouse before the morn. Every moment dies a man, every moment one is born." So keen a statistician was Babbage that he could not contain himself. He dashed off a letter to Tennyson explaining that because of population growth, the line should read, "Every moment dies a man and 1 1/16 is born." I may add that the exact figure is 1.067, but something must be conceded to the laws of meter.
In the 19th century, scholars all over Europe did amazing work in measuring their societies. They were hoovering up data on almost everything. But numbers alone don't tell you anything. You have to analyze them. And that's what makes statistics.
When the first statisticians began to get to grips with analyzing their data, they seized upon the average, and they took the average of everything. What's so great about an average is that you can take a whole mass of data and reduce it to a single number. And though each of us is unique, our collective lives produce averages that can characterize whole populations.
I looked in my local newspaper one week and saw a pensioner had accidentally put her foot on the accelerator and crushed her friend against a wall. Devastating, hideous, horrible thing to happen. And then there was a second one about a young man who didn't have a driving license, was driving a car under the influence of drugs and alcohol, and he bashed into a pedestrian, killed him. What's remarkable, absolutely remarkable, if you look at the number of people who die each year in traffic crashes, it's nearly a constant. What? All these individual events, somehow when you sum them all up, there's the same number every year. And every year, 2.5 times as many men die in traffic crashes as women, and it's a constant. And every year, the rate in Belgium is double the rate in England. There are these remarkable regularities, so that these individual particular events sum up into a social phenomenon.
Let's see what Sweden have done. We used to boast about fast social progress. That's where we were.
In my lectures, to tell stories about the changing world, I use the averages from entire countries, whether the average of income, child mortality, family size, or carbon output.
Okay, I give you Singapore, the year I was born. Singapore had twice the child mortality of Sweden. It's the most tropical country in the world, a marshland on the equator, and here we go. It took a little time for them to get independent, but then they started to grow their economy, and they made the social investment. They got away malaria. They got a magnificent health system that beated both US and Sweden. We never thought it would happen, that they would win over Sweden. But useful as averages are, they don't tell you the whole story. On average, Swedish people have slightly less than 2 legs. This is because a few people only have 1 leg or no legs, and no one has 3 legs. So almost everybody in Sweden has more than the average number of legs. The variation in data is just as important as the average.
But how do you get a handle on variation? For this, you transform numbers into shapes. Let's look again at the number of adult women in Sweden for different heights. Plotting the data as a shape shows how much their heights vary from the average and how wide that variation is. The shape a set of data makes is called its distribution.
This is the income distribution of China, 1970. This is the income distribution of the United States, 1970. Almost no overlap. And what has happened? China is growing, it's not so equal any longer, and it's appearing here, overlooking the United States, almost like a ghost, isn't it? Huh? It's pretty scary.
The statisticians who first explored distribution discovered one shape that turned up again and again. The Victorian scholar Francis Galton was so fascinated, he built a machine that could reproduce it. And he found it fitted so many different sets of measurements that he named it the normal distribution. Whether it was people's arm spans, lung capacities, or even their exam results, the normal distribution shape recurred time and time again. Other statisticians soon found many other regular shapes, each produced by a particular kind of natural or social processes. And every statistician has their favorite.
The Poisson distribution, the Poisson shape, is my favorite distribution. I think it's an absolute cracker.
The Poisson shape describes how likely it is that out of the ordinary things will happen. Imagine a London bus stop where we know that on average we'll get 3 buses an hour. We won't always get 3 buses, of course. Amazingly, the Poisson shape will show us the probability that in any given hour we will get 4, 5 or 6 buses or no buses at all. The exact shape changes with the average. But whether it's how many people will win the lottery jackpot each week or how many people will phone a call center each minute, the Poisson shape will give the probabilities.
The wonderful example where this was applied to in the late 19th century was to count each year the number of Prussian officers, cavalry officers, who were kicked to death by their horses. Now, some years there were none, some years there were 1, some years there were 2, up to 7, I think, one particularly bad year. But with this distribution, how many years there were with 0, 1, 2, 3, 4 Prussian cavalry officers kicked to death by the horses beautifully obeyed the Poisson distribution.
So statisticians use shapes to reveal the patterns in the data. But we also use images of all kinds to communicate statistics to a wider public. Because if the story in the numbers is told by a beautiful and clever image, then everyone understands. Of the pioneers of statistical graphics, my favorite is Florence Nightingale.
There are not many people who realize that actually she was known as a passionate statistician and not just a lady of the lamp. She said that to understand God's thoughts, we must study statistics, for these are the measure of his purpose. Statistics was for her a religious duty and moral imperative. When Florence was 9 years old, she started collecting data. Her data was different fruits and vegetables she found, put them into different tables, trying to organize them in some standard form. And so we have one of Nightingale's first statistical tables at the age of 9.
In the mid-1850s, Florence Nightingale went to the Crimea to care for British casualties of war. She was horrified by what she discovered. For all the soldiers being blown to bits on the battlefield, there were many, many more soldiers dying from diseases they caught in the army's filthy hospitals. So Florence Nightingale began counting the dead. For 2 years, she recorded mortality data in meticulous detail. When the war was over, she persuaded the government to set up a royal commission of inquiry and gathered her data in a devastating report. What has cemented her place in the statistical history books are the graphics she used, and one in particular, the polar area graph. For each month of the war, a huge blue wedge represented the soldiers who had died from preventable diseases. The much smaller red wedges were deaths from wounds, and the black wedges, deaths from accidents and other causes. Nightingale's graphics were so clear, they were impossible to ignore.
The usual thing around Florence Nightingale's time was just to produce tables and tables of figures. I mean, absolutely really tedious stuff that, unless you're an absolutely dedicated statistician, it's really quite difficult to spot the patterns quite naturally. But visualizations, they tell a story. They tell a story immediately. And the use of color and the use of shape, you know, can really tell a powerful story. And nowadays, of course, we can make things move as well. Florence Nightingale would have loved to have played with. She would have produced wonderful animations. I'm absolutely certain of it.
Today, 150 years on, Nightingale's graphics are rightly regarded as a classic. They led to a revolution in nursing, healthcare, and hygiene in hospitals worldwide, which saved innumerable lives. And statistical graphics has become an art form of its very own, led by designers who are passionate about visualizing data.
This is the billion-pound O-gram. This image arose out of frustration with the reporting of billion-pound amounts in the media. 500 billion pounds for this war, 50 billion pounds for this oil spill. It doesn't kind of make sense. These numbers are too enormous to get your mind round. So I scraped all this data from various news sources and created this diagram. So the squares here are scaled according to the billion-pound amounts. When you see numbers visualized like this, you start to have a different kind of relationship with them. You can start to see patterns. You can see the scale of them. Here, in the corner, this little square, 37 billion, that was the cost, the predicted cost of the Iraq War in 2003. And as you can see, it's grown exponentially over the last few years, so the total cost now is around about 2,500 billion. It's funny, because when you visualize statistics like this, you understand them. And when you understand them, you can really start to put things into perspective.